Okay, so I'm going to talk about some theoretical work stemming from the recent observation of the photon ring around M87. And it's been a very fun collaboration between a group of observers and theorists, which has implications both for our understanding of black holes and for future VLBI, which is very long baseline interferometry observation of black holes. And here is the list of collaborators. Everyone in blue is a member of the Event Horizon Telescope collaboration. And then this Harvard postdoc, myself, another Harvard postdoc, and Dan Capetz, who's a postdoc at IAS. I had a hard time deciding which talk to give. I'm also doing some work on flat space holography, and I just want to say one word about that we've been studying operator product expansions, and they look like product expansions in two-dimensional conformal field theories. They're the celestial version of collinear singularities, but they're an infinite dimensional group of asymptotic symmetries that act, and they give you recursion relations, which in some cases completely determine the form of the operator product expansion. And I'll be talking about that. We'll have a paper soon, and I'll be talking about that at the TÜV conference. So there's the famous picture, which was released last April. I've been thinking about black holes for 40 or 50 years, as have many of you in this room. And now all of a sudden, there's a picture. And we're now talking about things that have been seen. And so we'd like to understand this picture, and we'd like to see what more we can say about it. And the basic story is that the black hole is in here, a tiny circle, maybe a 12th the size of this whole diameter. And some things we don't understand, for example, like if you look at the brightness asymmetry ratio between the brightest part here and the brightest part here, it's a factor of 10. And there's various explanations of that. We don't know which one is right. Hopefully, future observations will be able to tell. Now, what's even more surprising than that image is the image that was produced by many thousands of hours of teams of people working on GRMHD simulation, where they start with a model with some kind of plasma, obeying an equation with 10 or 15 parameters, all kinds of stuff swirling around a black hole. They run it for weeks, and they come out with an image. And here is an example of an image. And everybody who sees this image sees the same thing. And that is, what is this striking pencil-thin circle? Why do we have a pencil-thin circle around a black hole? And the size of this circle is about 5 times the diameter of the size of the Schwarzschild black hole. It's known as the photon ring. And why is it so bright and so thin? Now, it used to be, some decades ago, I would see a brain or a string, and I'd say, that's a black hole. Now I'm seeing a black hole, and I'm saying, that's a brain or a string. I mean, there must be some simple way of understanding why there is this light pencil surrounding the black hole, and does it play some, after all, we don't understand Schwarzschild black holes. We don't understand where the entropy comes from. We don't understand what the holographic representation is. And could it be that this bright pencil ring is important in that story? And this goes to show how important observation is in physics, even if it's very, very remote from the kind of thing we're doing. Because I think if we had been seeing these things on a regular basis in the sky for the last few decades, we would have been trying to understand how you think about this pencil ring. Now, the current state of the art in thinking about it is to write some computer program with 15 pieces, 15 free parameters, put it on a computer, assign 50 students and postdocs to it, and come out with a library of images. They have 60, 100 images, and almost all of them have this pencil ring in it, and hasn't been any concerted effort to understand why there's always a pencil ring. So there should be some kind of effective field theory of the pencil ring. We shouldn't need all that GRMHD to understand what the photon ring is about. And is there some kind of enhanced symmetry along that ring? Now, it's important to say that this ring has not been seen here. If you take this image and you put it in to the EHT template, you will get out that image because its resolution isn't that good. And one thing that's very surprising that will come back later, I think if I asked you, the audience, how much of the net luminosity is coming from that pencil ring, you'd say, well, most of it. But in fact, this is a rather accurate image. There's one white pixel for every unit of flux. And the net luminosity coming from this pencil ring is only about 10%. And most of it is in these what seem to be much fainter but much bigger arms. And this is an optical illusion, which took me some time to come to grips with. And it's because our eye likes gradients, and it picks out gradients. And as we'll see later, there's only a mild logarithmic divergence in the intensity along this ring, and most of the intensity is coming from there, which means that in this picture, what's mostly being seen is not the stuff from the pencil ring. So, hasn't been seen yet, but as I'll get to later, it's hoped that it will be seen soon. And what I'm going to report on is describing, getting something close to a more universal theory of the ring, and also how you might observe it with proposed extensions of the Event Horizon Telescope, which have already been made before we wrote this paper, in particular those which involve an EHT station at low Earth orbit, on geosynchronous orbit on the Moon, or at the second Lagrange point, where the James Webb Telescope is going. Now, this photon ring is something really fascinating, and I myself didn't understand it until some matter of months ago. If you look around a Kerr black hole, there is a region with the property, this shell region called the photon shell, with the property that every point in the region has a bound photon orbit going through it. That doesn't mean that every photon orbit going through it is bound. It just means that if you're at a point in that region, that in fact for every point in the region, there's one bound photon orbit. For Schwarzschild, this fat ring collapses into a sphere. Now, if you're an observer up here, what you see is, of course, you don't see the bound photon rings because they never get out to infinity. But if you perturb them a little, they suddenly escape. It's like an unstable critical point. They suddenly escape and they go out to infinity. And the ones that you see are, as I've denoted there, the ones that lie on, that cross the region where your line of sight crosses the photon So this observer, which I've written at 17 degrees, which is about the degree that we're observing M87, is seeing the region of the photon shell inside the dashed line. And so there's this region of bound orbits. Now, if we were doing some kind of ADS-3 black hole or just Kerr black hole, and we were pushing it to extremality, this region of the photon shell would include the near horizon region. So it's some relic of this important near horizon region that is persisting for all Kerr black holes, and so may play some role in understanding their quantum structure, though of course we won't observe that. Now the interesting and surprising thing, if you look at an eclipse of the sun, as you look around the circle around the eclipse, you're looking at a radius around the sun. But as you look at the radius of the photon ring, the ring that you see, you are seeing around the circle, the angle on the telescope screen, so the image of this from the photons that leaked off this, you're probing different radius. And so it's kind of like a holographic direction. These ones, the light ones, came from a region of higher redshift than the dark ones. So this direction is the direction of, the vertical direction is the direction of the RG flow. And that is simply because on the screen, the angle is determined by the angular momentum of the photon which escaped. And for every angular momentum, there's one and only one radius at which the bound orbit can exist. So already for Kerr, it's a very strange system. Now I just want to interject here a wonderful quote from Jim Bardeen, who wrote a truly amazing paper in the early 70s in which he understood many of these things. And I love this quote. It's conceptually interesting, if not astrophysically important, to calculate the precise apparent size of a black hole. Unfortunately, there seems to be no hope of observing this effect. And I think this holds out hope for string theorists. It seemed absolutely impossible in those days, not only that you would see a black hole, but that you would get precision measurements of the shape of the shadow, many, many orders of magnitude from what was thought to be possible in those days. Okay, now this photon shell, there we go. Okay, so this is from a homepage of Leo Stein, which is fun to play with. And I'm looking at one of the amazing things about these photon orbits is that in Boyer-Lindquist coordinates, and only in Boyer-Lindquist coordinates, the orbits are always at a fixed radius. And you can see as the radius gets smaller and smaller up to some critical point, the theta excursions get larger and larger, and we're about to reach the critical point here. All of these orbits are retrograde, and right there, that hole in the top is going to close up, and right now, there was an orbit that went with zero angular momentum, went over the North Pole, and now they're going around the other way, and getting less and less theta excursion. The angular excursion is around that way. And you can see that right at the very end, this is a black hole with a high spin. The last stable orbit is very near to the event horizon. So the space filled out by all those orbits is what's called the photon shell. Now, how does this give rise to the bright image? Well, what astrophysicists do is they simulate this fluid, this glowing fluid plasma around the black hole, and then to see what you're going to see at the telescope, you don't have to find every geodesic in the space-time. You're only interested in geodesics from points in the fluid that go out to the telescope, so you do this backward ray tracing from the observer, and you see there are three kinds. Here's one, a null geodesic that goes straight into the black hole. And then here's one that just misses it by a big margin, goes straight out to infinity. And here's one that comes pretty close to this critical photon shell here. Circles around, it can circle around any number of times depending on how close you are. The closer you get, the more it'll circle out. But if you don't hit it on the nose, it eventually goes back to infinity. If you go a little bit inside, it'll circle around a couple of times and then spiral into the black hole. If you hit it right on the nose, it'll go around forever. So there's an order parameter associated with this photon ring. If you ask for the null length between any 2 points in space-time as you approach this photon ring, it goes to infinity as you get on the photon ring. So it's not a critical phenomenon the way we usually describe it, but it has a lot of flavor of that. And there are also these Lyapunov exponents, which are very complicated functions in Kerr of the angle. For Schwarzschild, it's just the Lyapunov number is just a number. It's called the Golfond constant. It's e to the pi, or e to the minus pi. For Kerr, it's a much more complicated function of the angle. And they tell you if you perturb the geodesic a little bit away from the critical orbit, how rapidly it starts to, how big the instability is. And these Lyapunov exponents are going to be directly measurable in future extensions of the EHT. So in order to understand this bright ring, what I'm claiming is we don't need the 1,000 hours of GR-MHD, and we'll also see that the details, one thing's nice about this, is if we go back to this big image here, there's a lot of glowing gases around the black hole. We've never seen a black hole before. We don't know what that stuff is made of. We don't know how fast it's going. We don't know what its angular velocity is. So it's not teaching us very much about the black hole. We don't know whether this dim part here is because it could be a Schwarzschild black hole with rapidly rotating matter, or it could be a rapidly spinning black hole that's dragging the matter along with it. There are many, many parameters in describing the astrophysics stuff around the black hole, but these Lyapunov exponents are universal properties of the black hole itself. Now, if I imagine that Mark is a black hole and David standing right there, what happens is, first there's a direct image. Okay, it's a direct image. Then there's an image where light from David goes around Mark. Is she pointing this? Okay. Okay, the light from David goes around Mark, avoids Hiroshi, comes to me. That's this n equals 1 image. Then there's another image where the light comes in front of Mark, goes around in one full orbit, and comes back. That's the n equals 2 image. So in fact, you get a whole sequence from things outside the photon ring. You get a whole infinite, in fact, you get a whole, if you had a perfect telescope, you would get a whole infinite series of nested images of the universe converging on the outside of this line, which is the edge of the black hole shadow. On the inside, you would get another whole infinite sequences of things coming from the inside. So this surface clearly has some interesting geometry to it, and I don't feel we've fully captured why it's so incredibly interesting, but it's also fascinating that now we're seeing it in a very visceral fashion. So these multiple images, now if you have not localized objects, but a whole gas of stuff right around the ring, what you get is a sequence of a kind of wedding cake structure, a sequence of sharper and sharper rings. Now, even though these rings, self-similar sharper rings, and even though the shape of the ring, the shape of the n equals 0 ring, has no general relativity in it, it's complicated astrophysics, which will be many decades before we can understand, the way in which the way and the angular dependent manner in which the self-similar shape is reproduced depends only on general relativity. The black hole is the mirror, and so it's perfectly embodying those characteristics of general relativity. Now you'd say, okay, this is all beautiful general relativity, the wonders of the Einstein equation, we're never going to see this. Not so. And the reason we think we can see it is that VLBI is more like your eye than like a blurry photograph image. It measures Fourier components directly, which are then reconstituted into the image. And the longer the baseline, the sharper the Fourier components. So if you have a long baseline, for example, if you put another station up on the moon, you'll see the low images, the n equals 0 image will be completely washed out, and it will be dominated by the higher images. And so we made a graph of it. The EHT is down here. We only need to extend it a little bit. In fact, some members of the collaboration think it can already be dug out of the current data to see within the reams and reams of data that they have that there is an n equals 1 ring there. And here we see from low Earth orbits, we can already clearly see the n equals 1 ring. From medium Earth orbits, we can get to the beginning of the n equals 2 ring from the geosynchronous Earth orbits, also n equals 2 from the moon. We can clearly get in the middle of the n equals 2. We won't even be able to see the n equals 1 out there because it'll be washed out. And indeed, at the second Lagrange point, it looks like we can, where the James Webb is planning to put their telescope, and we're trying to get them to have something at a millimeter so we can synchronize it with the current EHT array. We should be able to see this n equals 3 image. So it's this really kind of phantasmagorical thing that these multiple images of the universe created by a black hole are actually going to be observable by putting dishes at far distances out in the, and I've only gotten out to the L2 orbit. Of course, when we go way out into space, we can hopefully do even more. So in conclusion, the photon shell around a black hole is really interesting, more interesting and confusing than I realized. I didn't really understand what it was before I started thinking about it, and it sort of escaped our attention, mainly because we haven't been looking at black holes. But when you look at them, they're the main feature, and they have a lot of fine structure, which, by the way, couldn't be dug out of the numerics. After we knew where it was, we could find pieces of it in the numerics, but it really takes some analytic analysis to understand. And it has Lyapunov exponents, it has diverging order parameters. There should be some kind of effective field theory way of describing it. And the best thing is that we're going to try to see it. And so I think this is an exciting thing, both for theorists and for the next generation of EHT extensions, which hopes to put, and we're now talking about where the stations should be put in order to maximize this view of the photon ring by EHT extensions in space. Okay, I got to stop there.
Thanks for a very inspiring talk. Questions? Yes, and
thanks, Andy. You had some comments about the photon shell in the near extremal limit vis-a-vis the inner ADS2, which I didn't understand.
So first of all, the photon shell is a region in phase space. It's not a region in space-time. So if we're going to talk about some near scaling to the photon ring, it has to be a scaling in phase space, because not every null geodesic which goes through the photon shell is part of the photon ring. And things like this have come before in the studies of black holes. And the statement I wanted to make here is I feel that it's somehow connected with the ideas that we all love to think of, which is that when you take the extreme limit, and which, by the way, there's a fighting chance, there's a good chance that M87 itself, the spin hasn't been measured, but that there's a good chance, mainly because of the really truly extraordinary jet which was observed in 1918, that it does have a very high spin, and that it does have an extreme region. And we're looking at what the signals of that are going to be. But this region fattens out when you go to extremality. It's just a one-dimensional shell at Schwarzschild, but at extremality it fills the near horizon region. So it's a kind of vestige. And that, of course, is what we need. We need some way of thinking about using all our wonderful holographic ideas to say something about Schwarzschild, and I think the photon shell is somehow a candidate for that. But that's like a very vague statement.
Thank you.
So, I missed something when you showed us the GRMHD simulation that you said was for Schwarzschild. Do you know how the pencil changes as you increase angular momentum?
This is for this is for 0.94.
This is for 0.94.
Yeah.
Okay.
And in the EHT paper, in the 5 papers or whatever, there are dozens and dozens of simulations. You can find some simulations in which there are no photon ring at all. They're rare. It's very hard. So this would be the RG flow direction. Again, you'd look at this and think it's angular around the black hole, but in fact, it's not. It's the radius of the black hole. So this would be probing the inner radius, and this the outer radius. And now it could be. It's hard to distinguish in these GRMHD simulations between a Schwarzschild black hole with a very rapidly rotating accretion disk, a relativistic accretion disk, and a spinning black hole with a co-rotating accretion disk. However, it's almost certain that M87 is rapidly spinning, because if it did have such a big, bright, that produced all this light, rapidly rotating accretion disk, and it's a very old black hole, it would spin the thing up as it fell in.
More questions, comments? Sasha?
how sensitive are these images to corrections to GR? So let's say you have.
Well, I assume that corrections to GR would be of order, well, this is, okay, it's a little bit big of a number for me to calculate, but you mean Planck scale corrections to GR? Yeah, high derivative collection, very, very small. M87 is huge. It's 10,000. It's 10 to the 4. There's something of order. If it's a dimension 6 operator, it's. If you could see the photons going around many, many times, but we're hoping on the moon to see n equals 3, so you would get a factor of 3. But again, if there is some sort of critical behavior on the ring, maybe something interesting could happen. I think it's an interesting question. So Sasha was talking about null geodesics and what happens along null geodesics in this matter, accumulating and integrating. So here you have a space-time with null geodesics that just go around and around in a circle and don't go out to infinity. I think very interesting things could happen on such null geodesics. So there is a divergence there, which could fight the suppression, but I'm not optimistic that at M87 we'll see Planck scale effects, though some people are.
All right, let's thank Andy again and have some coffee.